Maxwell Ahin, and I am a physicist, inventor, entrepreneur, and, well, I guess change maker. I'm 13, and I feel like I can change the world, and I've already started my positive stream of unlimited energy, so, you know.
So, do you think you can solve our energy crisis here on planet Earth?
I believe I will, and I believe I already have solved the main problem. Now it's just a matter of, getting this out there.
And what do you need to be able to get this out there? You just need somebody to watch this video and say, here's some money, or what do you need?
Well, all I can think of really is support.
First theorized the existence of gravitational waves in 1916, upending the world's understanding of physics. And now, after two massive black holes collided nearly 2 billion light years from Earth, astronomers at the LIGO Observatory in Washington state have detected a fourth set of these ripples in the fabric of space-time. Here to talk about this discovery is CBS News science and futurist contributor and theoretical physicist Dr. Michio Kaku. Professor Kaku, thanks so much for joining us.
Glad to be on the show.
So let's start with a basic definition here first. Can you explain what gravitational waves are?
Think of throwing a rock in a pond. The impact creates waves, ripples, which then begin to spread rapidly. Now, the pond is empty space, space-time. But it's like a fabric, says Einstein. So when you drop a rock on the fabric of space-time, it causes ripples that travel at the speed of light. So Einstein predicted it in 1916, but it took 100 years to finally prove that, bingo, Einstein was right after all.
Gravity is something incredibly commonplace. We're always dropping things, we're not flying off the surface of the Earth. It's a part of our lives from the moment that we're born. But it turns out it's a very mysterious and deep part of the universe. When something has mass, it has the ability to bend space.
In empty space, light travels in a straight line. But place something massive, like our sun, on the fabric of space, and its immense gravity warps space. The black hole's gravity is warping the fabric of space. Everything that travels through this curved space must follow a curved path, including light.
The amazing thing is that not only does gravity warp the light into the black hole, light coming from farther away gets bent around it. And so you could see this shimmering distortion in the stars in the background as a black hole moved in front. It would almost be like taking a piece of glass and moving it across the star field.
And it's not just space that the black hole is bending. Time is warping too.
In the 1950s and 60s, the United States Air Force did an experiment. They took the best atomic clocks they had, they synchronized them on the ground, they put one in a plane, flew it around the globe, the other one they left back at base. When they brought the two clocks back together, the clock that was up in the air ran fast. So what happens is gravity warps space and it causes clocks in weaker gravitational fields to appear to run fast. And this effect is proportional to the strength of the gravitational field. So if you were to hop in your spaceship, put yourself in orbit around a black hole, let's say maybe for an hour, so to you in your ship, an hour passes kind of boring. But when you leave the black hole, radio back to base, they tell you you've been away for 6 years. This is that gravitational field that is warping space. And because the black hole has such a strong gravitational field, that effect is huge.
During a total eclipse. And that prediction was verified, I think it was almost 5 years after Einstein wrote down his equation, and he became an overnight celebrity.
Yep. So we have a little picture just emphasizing what you described. So you can speak to it if you'd like. So you see the two images of the star, one coming from the fact that the trajectory of the light ray is bent as it passes by the sun, shifting its apparent position in the sky. And indeed, as you mentioned, Einstein calculated the angle between those two, and the observations confirmed it. And that was convincing.
I think the reason that the fact that Einstein explained something that was already known was less convincing than the prediction of something new was the natural tendency of people is not to trust the theorist.
One necessary result of the theory is that light should follow curved paths around massive objects. And a famous experiment observed light from a distant star curving around the sun during a solar eclipse, whereby the blocking of the sun's light allowed us to directly observe the light from the star behind, which appeared in a shifted location. When light is deflected around more compact objects, like black holes, the light from the more distant object can bend around the mass in a way that results in multiple images of the object. This phenomenon is called gravitational lensing.
It goes like this. Objects, you can bring the lights down a little if you will, like the sun or the planets, they warp the environment of space and time, and it's these warps and curves in space that are able to cause other objects to move along peculiar trajectories if you weren't aware of this picture. The metaphor that we love to use, it's imperfect to be sure, but if you think about space and time as sort of like a trampoline, you put some heavy object in the middle of it, it warps the surface, and then if you roll the marble goes into orbit, much like a planet would, much the same way the sun warps the environment, and then the planets go into the orbital trajectories that we are familiar with. That was kind of a post-diction explaining a puzzle that was already known observationally, but then he was able to go further and make a prediction for something that had not yet been seen. And indeed, that had to do with the bending of light by the sun. So if you have a distant star, it sends light toward the Earth, goes in a nice trajectory of that sort. But then later on, if the Earth is on the other side of the sun, and you now consider that starlight, according to Einstein's new picture, it's going to go in a curved trajectory as it goes through the curved environment surrounding the sun, and that has the effect of making the position of the star in the sky shift.
Some major science news to tell you about this great discovery that was predicted, in fact, by Albert Einstein himself 100 years ago. Imagine that. Scientists have detected evidence of an astronomical phenomena called gravitational waves. Hello.
Hello.
So who or what is this gravitational wave of which you speak?
Well, so, okay, here's a way to think about this that makes intuitive sense to me at least. The sun, when light comes off the sun, it takes 8 minutes to get to the Earth. And the Earth is held into its gravitational orbit by the sun. But what if the sun were to be moved suddenly? Would the Earth know about it right away, or would it take 8 minutes for the Earth to know about it, because nothing goes faster than the speed of light? Now, according to the old classical Newtonian physics, it would be instantaneous, but Einstein in 1915 said, no, gravity would also have to travel to get to the Earth, so there would be a delay. And so the traveling of gravity is something called a gravitational wave. And so this is a prediction that was made way back like 100 years ago, and now for the first time we've measured one, and so Einstein was right.
How did they detect these waves?
So they have these two observatories that are in the States, and they're 3,000 kilometers apart. And these things are super, super sensitive. And they have these lasers, and they're looking for wiggles and all these things. I mean, they've got to be super, super sensitive to the point that a truck driving by could set it off. And so the reason they have two of them 3,000 kilometers apart is because if they think they saw something, they want to be able to independently confirm it twice.
Like a backup, redundancy.
Exactly,
right.
Exactly.
Now in general relativity, it's not the distance between 2 points in space, it's the distance between two what we call events in space and time. So that little formula there encodes the geometry of Euclidean space. They would say, well, how do we describe, if we now have a surface that's got a complicated curvature, we want to generalize what Pythagoras did. This metric is a convenient mathematical way of doing it.
And here's one just example, just so people who are following the math can go along. Here's a curved shape, if you will, and the distance between the 2 points is no longer just delta x squared plus delta y squared square root, which is what we learned in junior high school, but rather is given by some unusually looking strange combination of delta x squared and delta y squared. And if you curve it a little bit differently, We learned that the distance between those 2 points might be given by this particular combination of delta x squared and delta y squared. And finally, just to get to what you're describing in the general case, we can have combinations that aren't even just delta x squared, delta y squared. We can have cross terms, like on the far right, delta x, delta y. And finally, to get to that object called G, the metric tensor, this is sort of a generalized version of the Pythagorean theorem where you're going to allow the surface to be curved. And that G thing there encodes the geometry that Franz is referring to, and Einstein gives us equations, those complicated equations that we saw before, where you can determine the shape of space-time if you understand the distribution of mass and energy.
By the idea that Newton had, which is the particles actually move in a path and they accelerate according to the force that they experience. And some particular, what Newton would have called the potential, was a part of the data which describes this fabric of space as a particular way that the fabric of space and time is curved. So you pick that term up and use that, and you show that the geodesic motion reduced to what Newton would have predicted. And so that is a check that it actually works. And
there it is right behind you for all those who want the
equation.
details to track two listeners. But again, the point is you can start, as Kerman said, with Einstein's equations and extract Newton's from them in this particular limit. So, Samir, just can you give us a moment of sketch of what the inflationary theory is telling us?
Yeah, it's a very interesting situation that our universe looks so homogeneous and so flat. But if we just start from first principles, it's not clear why everything should be so homogeneous everywhere. Because after all, what you see on one edge of the universe has never had any time to talk to what's happened on the other edge of the universe, because light hasn't had time to go from here to there. So why does everything look the same on all the sides? And so the idea was, if we start with the universe which was very tiny, the size of about a marble, and then suppose it just grew from there very fast, and all that we see today really came from one marble, which in fact could have talked to each other all over, then we could sort of explain why everything was so homogeneous. And because the whole marble just expanded, when you stretch something, it just becomes flattish, and that's why the whole universe is so flat. So it explains the vastness of our universe, why there's so much stuff there, why it's so homogeneous. It's really a very remarkable idea.
Beautiful observations of this bath of microwaves that are arriving to Earth, but are actually they're everywhere, and they are at the same temperature here and there. That's the best evidence we have of this inflationary period. But it's not exactly the same. It's actually slightly different in a part of a million that can be explained.
Which are the little speckles that people are seeing up here.
Those differences in the Earth are very, very small differences. Like I said, they're parts in a million, but they can be detected. They have been measured.
Temperature differences from places.
Temperature differences, right. Difference in the temperature of these microwaves. And that can fit beautifully to theory. All these bumps are predicted by the theory, and all the experimental points follow it beautifully. So we are in what we call now an era of precision cosmology, in the sense that there are many constants, parameters that tell us about cosmology that we know very precisely. We don't always understand where they come from or what they mean, but we can measure them to a part in 1,000.
You're co-director of Columbia's Institute for Strings Cosmology and Astroparticle Physics.
Yes.
It's a pretty good pickup line. Now, since last we were together, scientists detected gravitational waves. I understand this is something Einstein predicted.
This is a huge discovery, not only confirming Einstein's ideas, but opening a whole new way of exploring the universe.
What is a gravitational wave, and why does it sort of change everything?
So a gravitational wave is actually a ripple in the fabric of space. And what happened is, this is 1915, he doesn't just stop, he keeps going. And a year later, he realizes that if space is like a trampoline, then imagine kids running around on a trampoline. They're going to send ripples on the surface. So he says the same should be true of the fabric of space. If you've got two rapidly orbiting stars, neutron stars or black holes, his math predicts that they will generate a steady march of ripples in the fabric of space. Those
are gravitational waves that he predicted mathematically. His math shows that as a gravitational wave ripples by anything, it will stretch it and compress it. You see it happening
like the
to
Earth.
the Earth right here.
So literally, because we're part of the fabric of space-time, you and me and the Earth is stretching and compressing along with the rippling of space-time.
That's exactly right. Now, the one thing is this is exaggerated
I hope
little
so.
bit. The ripples would actually cause the Earth to stretch and compress by less than an atomic diameter.
Universes and infinite parallel universes constantly being created is literally flow of reality and time as we know it. So technically there's a universe in which God can exist, right? So like as your book suggests, God is everything because of E equals mc squared. Literally God is within and can be everything. There is an infinite possibility that there's a parallel universe in which God does not exist or is more powerful. In other words, point about that is that that means that there is power that is greater than God. And considering that there is an infinite number of vibrations and therefore an infinite number of realities within our dimensional space, or I guess altered dimensional space, considering that they're either higher or lower, still in the same confined space, there is an infinite number of parallel realities with an infinite number of parallel dimensions that actually can create a powerful or less powerful form of God E equals mc squared as we know it.